Now we're in homework 6, problem 1. In this problem, we have two variables, x and y, and they have joint density function. This is the joint density function, and fxy equals to this. And we have absolute x less than 1, and absolute y is less than 1. 0 otherwise. So we have this condition, and in the first question we need to find a. We will find a so that this is a valid joint density function. So according to the definition, it is the valid joint density function when this guy equals to 1. So we just use integral transmission and calculate this formula, and finally we got a equals to 4. So it's an easy question. Now in the second question, we need to prove or disapprove that whether x or y, x and y are uncorrelated. So in order to answer this question, we need to calculate the value of the expected value of x multiples y, and x and y. So first we calculate this, and we just use the form the equation, and finally we got the expected value of x multiples y equals to 1 divided by 9. And now we need to calculate the expected value of x, and we got this guy equals to 0, and because they are symmetric, so y, the expected value of y should be 0 too. No matter what the value of y is, the expected value of x multiples y isn't equal to the expected value of x multiples the expected value of y. So because of that, x and y are not correlated. So this is the second question. And in the third question, we know that the x and y are joint density function, and they are jointly normal. And also we have proved that x and y are not uncorrelated. So it's very easy for us to get x and y are not independent. It has been proved in the resources by definition. So it's an easy question. And now in the next question, we need to find the joint density function of the square of x and the square of y. So we can set other two variables, z and w, omega. We can call it omega. Okay, so according to the definition, we have got the j is that matrix, the integral transmission of z and x and z and y, omega x and omega y, and we got the matrix. The matrix is this, and j equals to 4xy. So we got this, and also we have the integral z is no less than 0 and less than 1, and omega no less than 0 and less than 1. It's from the x and y. So the absolute matrix should be 4. For this is like this. So the root of z and the root of omega. So this is the absolute matrix. So now we can calculate the density function of z and omega, and from the definition we know that because the number of roots should be 4, x, the square of x and square of y. So we can get this equation. We have four guys, and we just plus them, and we got this. We just put the root of z and root of omega into the density function of x and y, and we have this, and finally we got this joint density function should be like this in this integral. So that's the fourth question, and also otherwise this guy should be 0. So that's the fourth question. And now in the last question, we need to prove or disprove that the square of x and the square of y are independent. So from the fourth question, we have the joint density function of z and the omega should be like this. And also because x and y are because they are jointly normal, so we can easily got that the density function of z and density function of omega should be like this. So we divided them, and we know that the joint density function of z and omega should be the value of the density function of z multiples the density function of omega. So actually from this we know that z and omega are independent, and we got this. So the square of x and the square of y are independent. So that's the last question, and this is the whole story of the problem 1.